Hi students, welcome to Sunil's tutorial. I'm Sunil Nirwani and today we'll be doing magnetic effect of electric current. Today we will see how we could find out the magnetic field in a long straight solenoid. Now before that I need to know what is a solenoid. Now a solenoid is nothing but a tightly wound helical loop of insulated wire such that its length is comparable to the radius. That means, suppose if I had a magnetic material here, and if a wire was wound, an insulated wire was wound on it, then that would constitute a solenoid. So what is a solenoid? A solenoid is nothing but a tightly wound helical loop of insulated wire such that its length is comparable to the radius, right? Alright, what is a solenoid? A solenoid is a tightly wound helical loop of an insulated wire, tightly wound helical loop of an insulated wire such that the length is very large, and comparable to length is very large as compared to its radius. Length is very large as compared to its radius. So that is what is a solenoid. Now let's try to find out the magnetic field due to a long straight solenoid. Magnetic field due to a long straight solenoid. Right? Now let's see this. Let's first draw a solenoid, guys. Please draw the diagram. Let's assume current I enters from here. This point is A. You have this point is say B. Current is going to be moving through the wires and current is out from here, right? This is going to create a magnetic field around it. Let's consider this as C and this as D, right? So let us consider a very long solenoid. Consider a very long solenoid. Now for such a solenoid I can say that for such a solenoid, what are the various things that I have? I'll have the magnetic field inside will be uniform. The magnetic field inside is uniform. Same conductor, same length. The direction of the magnetic field can be given by the right hand rule. The direction of magnetic field can be given by a right hand rule. And the third thing, the strength of the magnetic field at any point outside it is almost zero. These are the three things that work with the solenoid. The strength of magnetic field outside, at any point outside, the solenoid is almost zero. Right? So these are the conditions of a solenoid. One, the magnetic field inside it will be uniform. Second, the direction of the magnetic field can be given by the right hand rule. Third, the strength of the magnetic field at any point outside will be approximately equal to zero. Now let us consider N is the number of turns of coil wound per unit length. Number of turns of coil wound per unit length. Right? Let us assume that I is the current passing through the coil and L is the length of the solenoid. Right? Now, the magnetic field produced by the solenoid is similar to that produced by a magnetic dipole, right? So let us assume that B bar or B vector is the field produced by the solenoid, is the magnetic field produced by the solenoid. Right? Current flows through a conductor, gives rise to a magnetic field. Right? Now, in order to find out what is the strength of the magnetic field, let us consider a closed loop. Let us consider a closed loop ABCD. Consider, instead of ABCD, B I am using as magnetic field. Let's relabel this instead of ABCD, because B is strength of the magnetic field only, it will only create confusion. We'll label it as PQRS. So labeling it as ABCD, let's label this as PQRS. So let's consider a closed loop PQRS. Right? Now, L is the length of the solenoid. PQ is the number of turns enclosed by the rectangle PQRS. I can say that the number of turns in length PQ of the solenoid. We had said that N is the number of turns per unit length. Therefore, the length of the solenoid is L. So, in that case, the total number of turns will be N into L. Fine, do we get this thing clear? Now, I is the current that is in the threads of the rectangular path. Therefore, I can say that the total current threading in the rectangle, the total current threading in the rectangle you have, guys, see this. You have a current of I flowing through each of this thread. The length of the solenoid is L. There are n number of turns, right? So the total current is going to be nothing but N into L into I. This is my total number of turns multiplied by the current in each turn, right? Do we get this simpler? Now, if I apply Ampere's law to this, if I apply Ampere's law, you can say by Ampere's law, if I apply Ampere's law to this, then what we get is that the line integral of the magnetic field B, line integral of magnetic field B along rectangle PQRS should be equal to mu 0 times the current. Yesterday we had, or last lecture we had seen this, that line integral is mu 0 times current. The total current we found out is nothing but N into L into I. So that is going to be my line integral. So I can say that thus line integral is integral of B vector dot dl for PQRS is going to be equal to mu 0 NLI. This is going to be my line integral. Fine, do we get this in here? Now, if I want to find out the line integral for this whole rectangle, then I'll have to find out the integral in each part of the rectangle. Now, if I split this up by integration, this can be written as what integral of B vector dot dl in PQRS should be nothing but the integral of PQ B dl, the integral of the length plus integral of QR B dl plus integral of RS B dl plus integral of SP B dl. That is going to be my integral in the rectangle, right? Now, I can say that the direction of B vector in QR, you have QR and you have PS, you have SP, right? So in that case, I can say that the direction of B vector in QR and SP will be opposites. They are opposite in direction, therefore I can say that integral of QR B dl should be equal to integral of SP B dl should be equal to 0. Why will they be equal to 0? Because the direction of B vector is perpendicular to them, and if it is perpendicular, we know that cos 90 is 0, because B vector is perpendicular to QR and B vector is perpendicular to PS, right? So therefore theta becomes 90 and therefore these two values will become 0. Now I can say, since as for the solenoid the length is much larger than the diameter, therefore I can say as the length of the solenoid is much larger than the diameter, therefore you could say that integral of the magnetic field at a point outside the cylinder will practically be equal to 0. The magnetic field at a point outside the cylinder will approximately be equal to 0. So at a point outside the cylinder will approximately be equal to 0, which is the point outside the cylinder, SR. Therefore I can say integral of, we have said, RS BdL should approximately be equal to 0, right? Now if I substitute this, then I can therefore say that integral of PQRS BdL is going to be nothing but integral of PQ BdL plus 0 plus 0 plus 0. We already proved that QR, RS and PS all three are going to be equal to 0, right? So this is going to be equal to integral of PQRS BdL is going to be integral of PQ BdL, right? Now the axis of the solenoid, that is B vector and dl, are in the same direction. Therefore the angle between B and dl has to be 0. See guys, B vector, this is the magnetic field B vector. B vector is in this direction, dl is also in the same direction, right? I can say that along the axis of solenoid, B vector and dl are in same direction. Therefore angle between them is 0. If the angle between them is 0, that means I can say that integral of PQRS B vector dot dl is going to be equal to integral of P to Q. Dot product of two vectors is nothing but the magnitude of two vectors, and cos of the angle between them is going to be nothing but B into dl into cos of 0. Cos of 0 is nothing but 1. So this is going to be integral of P to Q B dl. B is a magnetic field. The strength of the magnetic field is going to remain constant. Whatever is constant comes outside the integral. PQ dl, right? Integral of dl, if I join all the small length, I'll get the total length of the conductor, right? But I can say that integral of PQ dl is nothing but the length of the conductor. Therefore I can say that integral of PQRS B vector dot dl is nothing but D into L, right? Once you have this, substitute this in your Ampere law. If I substitute this in your Ampere law, you will get this as, if I substitute this in the Ampere law, I'll get, see, my Ampere law I stated was integral of PQRS B vector dot dl vector was mu 0 nli. This can be substituted as BL. So BL is mu 0 nli, right? So in which case I will therefore get L and L gets cancelled. You will get magnetic field in the solenoid is mu 0 n into I. So the strength of the magnetic field in the solenoid depends upon the permittivity of free space, number of turns and the current flowing through the solenoid. Fine, do we get this in here? So the magnetic field in the solenoid is directly proportional to the number of turns and directly proportional to the current flowing through the solenoid. Now at the ends of the solenoid, the magnetic field will be given by, magnetic field at the end of the solenoid is half mu 0 Ni, right? That will be the magnetic field at the ends of the solenoid. Fine. So do you understand the solenoid and the working of the solenoid? Next, let's try to see the construction of a moving coil galvanometer. Moving coil galvanometer. Let's see the construction and the working of a moving coil galvanometer. Please copy. Please draw the diagram. Done. Right, take another question for this. Give the construction of a suspended coil type moving coil galvanometer. This is the diagram for a suspended coil type moving coil galvanometer. Moving coil galvanometer. Suspended coil type moving coil galvanometer. Now let's see the construction, guys. Can you please see this? It consists of a rectangular coil of thin insulated copper wire. This is your rectangular coil of thin insulated copper wire, which is suspended between two cylindrically concave pole pieces of a horseshoe magnet. These are the magnets. So this is your coil on which you have an insulated wire which is suspended between two poles of the magnet. C is the soft iron cylinder that is placed at the center of the coil, so that you have a magnetic field generated here, right? Between the poles. The coil is suspended by means of a thin fiber of phosphorus bronze strip. This particular strip that you have is your phosphorus bronze strip. That's the material that is used for suspending the coil. The reason why we use phosphorus bronze strip, because it has good elastic properties. right? And it is a good conductor. Current enters uh, current enters the coil through this thin suspension fiber and leaves through the spring that is attached at the end, right? A small mirror is fixed on the suspension. This is your mirror that is fixed onto the suspension to measure suspension coil, and it is used to measure the rotation of the coil. That's it. And the spring is used to bring the coil back to its original position when current is not flowing through the coil, right? Can you just write this construction down? It moving coil galvanometer. It consists of a rectangular coil of thin insulated copper wire, and it is suspended between two cylindrically concave poles pole pieces of horseshoe magnet. Pieces of horseshoe magnet. Right, that was your rectangular core which has been suspended between this horseshoe magnet. C is the soft iron cylinder core fixed at the center of the coil. Now, the core is suspended by means of a thin fiber of phosphorus bronze suspension. Having good elastic property. Right, the current enters the coil through the suspension fiber. Current enters coil through suspension fiber and leaves the coil through the spring attached at the other end. Leaves the coil through the spring attached at the other end. Right? Last thing that you need here is the mirror. A small plane mirror is fixed on the suspension fiber. And it is used to measure the rotation of the coil. and that's your construction of a moving coil galvanometer. I think we've stopped this here for the day. Thank you very much.